12 light-years from Earth, a dim orange-red star casts a harsh glare into the surrounding vacuum. This is the Epsilon Indi system. For decades, our catalogs of alien worlds have carried a built-in bias. Direct imaging has typically only worked for young, blazing hot gas giants that glow fiercely from their recent, violent formation. Older, colder planets are practically invisible. They emit very little thermal energy of their own, and any faint signal they do release is entirely swallowed by the blinding radiation of their host sun. To understand the physical scale of this problem, imagine trying to spot the faint greenish glow of a single firefly. Now imagine that firefly is resting on the lens of a massive lighthouse, and you are trying to photograph it from miles away. Because of this optical barrier, true Jupiter analogs, massive, cold gas giants orbiting far from their stars, have remained an invisible missing piece in our map of the cosmos. Breaking that barrier required a machine designed specifically to catch the faintest infrared signals in the universe, the James Webb Space Telescope. To capture enough of those rare, faint photons, Webb relies on an enormous collection area. In this photograph, you can see technicians standing beneath the telescope's primary mirror, a massive array of gold-coated hexagons spanning over 21 feet across. But a giant mirror alone cannot pierce through stellar glare. The actual solution lies inside Webb's mid-infrared instrument, or MIRI, which carries a highly specialized piece of hardware known as a coronagraph. A coronagraph is essentially a physical shield. When the telescope points at a star system, a mechanical black disk slides perfectly into position, artificially eclipsing the host star and blocking its overwhelming light. The moment that blinding radiation is cut off, the hidden environment around the star is suddenly exposed. And in the Epsilon Indi system, Webb sensors picked up a faint, ghostly signature. They found a planet, Epsilon Indi Ab. This world sits far out in the freezing dark, orbiting its star at roughly 4 times the distance Jupiter sits from our sun. This diagram illustrates just how massive this new planet is. On the left is our Jupiter, and on the right we see the equivalent of 7.6 Jupiters stacked together to match the immense weight of Epsilon Indi Ab. But it doesn't take up more space. All of that extreme mass compresses down into a single sphere the exact same diameter as our own Jupiter, making this alien world incredibly dense. It is also remarkably cold. The surface temperature hovers between -70 and 20 degrees Celsius. At those temperatures, the planet isn't reflecting much starlight. The faint signal Webb captured is actually residual thermal heat, the fading embers left over from the planet's birth billions of years ago. You have a hyper-dense sphere, radiating the last lingering heat of its ancient formation into the cold vacuum. Epsilon Indi A is a physical paradox, an ancient, freezing ember that defies our standard expectations for gas giants. While the primary mirrors capture raw light, the telescope's internal instruments act as chemical sensors, dissecting that light to reveal the atmospheric makeup of alien worlds. To study this cold super-Jupiter, the research team applied an 11.3 micrometer filter to their sensors, scanning the light spectrum specifically for the signature of ammonia gas. Ammonia is a defining chemical for these planets. As we see in this image of our own Jupiter, those distinct swirling upper atmospheric bands are completely dominated by ammonia clouds. We expected to find the exact same chemical marker on Epsilon Indi A. Instead, the data came back empty. The expected light signature for ammonia was completely missing. The planet has the mass to hold on to that gas, which led the team to a new hypothesis. The ammonia is being hidden. They believe the planet is shrouded in thick, patchy clouds of water ice that are physically blocking our view of the layers beneath. The presence of high-altitude water ice reveals new layers of complexity that our existing computer models do not yet capture. As we refine our techniques, we are left to wonder what else is swirling in the dark, violent bands of Epsilon Indi Ab. Astronomers recently managed to do something incredibly difficult. By placing a dark disk called a coronagraph over a star to block its blinding light, they isolated the faint glow of a super-Jupiter called Epsilon Indi Ab, hiding in the dark. Based on everything we know about cold gas giants like our own Jupiter, Epsilon Indi Ab should be completely drenched in ammonia gas. This chart shows the spectrum analyzed by the James Webb Space Telescope. Researchers targeted 11.3 micrometers because ammonia molecules absorb light exactly there. Every model predicted a huge, unmistakable dip at this point, but the reading barely registered. The giant ammonia signature was completely missing. The team at the Max Planck Institute for Astronomy was stunned. Their sophisticated, multi-million-dollar predictive models were totally wrong. A missing chemical signature of this magnitude leaves astronomers with two difficult choices. Either our basic understanding of gas giant chemistry is flawed, or there's a massive, undiscovered physical feature wrapping around the planet, actively blocking the ammonia from our view. The researchers quickly ruled out the idea that the gas had vanished. Instead, they deduced that the ammonia was still there, but physically hidden beneath a thick, opaque layer higher up in the atmosphere. The missing ammonia signal is actually being blocked from our view by towering, massive clouds made entirely of water ice crystals. If you want to picture them, look up. They are essentially alien versions of the high-altitude, wispy cirrus clouds we see floating through Earth's skies. Finding these structures upgrades Epsilon Indi Ab from a predictable ball of gas into a world driven by a complex meteorological engine. Epsilon Indi Ab actually sits between 200 and 300 Kelvin, roughly -70 to 20 degrees Celsius. That makes it significantly warmer than our Jupiter, mostly because it's still holding on to ancient heat left over from its formation billions of years ago. That residual internal heat actively prevents the formation of the upper layer ammonia clouds that we see on Jupiter, which allows these water ice clouds to dominate the upper atmosphere instead. But these water ice clouds don't form a solid shell. They're swirling, chaotic structures that create a fractured, patchy shield all the way around the planet. This uneven barrier entirely changes the planet's energy balance. It traps the lingering formation heat in some regions while allowing violent leaks of thermal radiation to escape into space through the gaps. Historically, astronomers have simply excluded clouds from their exoplanet computer models. The math behind unpredictable, shifting weather is incredibly difficult to simulate. But the sheer scale of the ice clouds on Epsilon Indi Ab proves that alien weather is a physical reality that atmospheric models have to account for moving forward. While the James Webb Space Telescope successfully detected the interference from these clouds, this is only step one in mapping exoplanet meteorology. The next major leap in astronomical technology is already on the horizon, with the Nancy Grace Roman Space Telescope, slated to launch around 2026 or 2027. This upcoming observatory is designed specifically to directly detect highly reflective atmospheric features, giving us a much clearer look at these alien ice clouds. This tool allows astronomers to move from simply weighing distant planets to documenting their daily weather patterns. Decoding the chaotic weather of giant, distant worlds like Epsilon Indi Ab is the mandatory foundation we have to build. Only then can we hope to identify the delicate, life-sustaining atmospheres of Earth-like worlds hiding out there in the dark.